Good day, everyone. You are once again welcome to the Academy channel. This video will be looking at chemical kinetics, which is another way of calling rate of reaction. Chemical kinetics. Or rate of reaction, anyone you want to call it. Now, in this part of chemistry, we want to look at how fast are the reactions going. When you react to things, how fast will they react? Unlike chemical equilibrium, where we looked at how far, but here we're looking at how fast. So there are so many factors that can increase or decrease how fast a reaction will go. So in other words, we can say that we have factors that affect the rate of chemical reaction. We have factors like pressure. We have pressure. We have temperature. We have nature of reactants. Nature of reactants. We have catalyst. And lastly, we have concentration. Now, all these factors, once they are increased, of course, the rate of the chemical reaction will also increase. If pressure is increased in a reaction, or let me say pressure of reactants are increased, the rate of collision of the reactant will also increase. So eventually the rate of reaction increases. And when pressure is decreased, the rate of collision decreases, rate of reaction also decreases. Now, temperature. Reaction occurs faster at higher temperature than at lower temperature. Nature of reactant. Reactant can exist. It is a state function. Nature of reactant is a state or phase function because you can have reactant at either solid, liquid, or gaseous state. Reaction react faster in their gaseous form than other forms. It also reacts faster in liquid and solid. So coming from gases down to solid, it decreases like that. So when the phase of reactant is in solid, reaction will be very slow. When you increase to liquid, it becomes faster, and in gases, it's fastest. Then catalyst. Catalyst also increase the rate of reaction by lowering the activation energy or providing an alternative path for the reaction to reach the production of products. Now, lastly, concentration, which is where we are actually going in this particular topic. Concentration. Unlike others, one would have thought that once concentration is also increased, rate of reaction will also increase. But there are so many other factors we have to consider if we want to check if increase of concentration will eventually also increase rate of reaction. So let's check concentration. Concentration. Now, basically, we have rate of reaction R, rate of reaction mathematically. Rate of reaction R is equals to concentration over time. Concentration of reactant divided by time. This is how the rate of reaction is expressed mathematically. Now, this is not just what we'll be looking at. Because if you are looking at this, one would think that in this particular expression, rate of reaction is at least proportional to concentration. So once concentration is increased, rate of reaction increases. No, this is not just what we'll be looking at. There is a particular equation we call rate law. Rate law. Rate law is an equation that is showing the relationship between rate of reaction, specific rate constant, and concentration of reactants. Rate of reaction, specific rate constant, and concentration of reactant. What do I mean by this? If you have reaction A, like this, plus these are coefficient. A is a coefficient, B is also a coefficient. A is reactant, B is also a reactant. Capital letter A is reactant, capital letter B is a reactant. Small letter A is the coefficient of reactant A. Small letter B is the coefficient of reactant B. To give products of D, or let me say C rather, C, plus D and D. C is the coefficient of product C, while small letter d is the coefficient of product D in capital letter as well. Now, if you want to write the rate law for this particular equation, we have said rate is directly proportional to concentration of reactant. Concentration. Although we are not supposed to write concentration again because square bracket alone, this square bracket, anywhere you see square bracket indicate concentration of whatever that you have inside it. So we can write this as, let's write rate law in respect to reactant A first. It means R, or rate law, is directly proportional to concentration of A, like this. And we can rewrite as R is equals to K concentration of A raised to power X. I know you'll be wondering where this X came from. Now, the introduction of K is because we remove proportionality sign. When you remove proportionality sign from an equation, you have to introduce a constant. So this R represents rate law. So, or rate rather. We can just say rate. Rate R is equals to K concentration of A raised to power X. Now, like I said earlier, we cannot just say when we increase the concentration of reactant, the rate of reaction automatically increases. Why? Because there's something we call reaction paths. Reaction paths. This reaction path is the one explaining what we refer to as order of reaction. Order of reaction. And we have several order of reaction. We have reaction that occurs at zero order. We have reaction that occurs at first order. We have second order. We have third order. But for this video, we'll only be explaining zero and first order. So in subsequent videos, I will explain second and third order. Now, if you look at the expression that I have, R equals Kx. X was not in the initial equation, but now we have introduced X. This X is what represents order of reaction. Order of reaction. Now, it looks like we have brought X in from somewhere else. No. It is just to let you know that the order of reaction cannot be determined stoichiometrically. It can only be determined experimentally. So this means looking at a balanced chemical equation, one would not know the order of reaction. The only thing you can suggest from a balanced stoichiometric equation is molecularity. If the reaction depends on just one reactant, you can call it unimolecular reaction. If the reaction depends on two reactants, you can call it bimolecular. If it depends on more than two, you can call it termolecular. So it is only molecularity that we can determine from a balanced stoichiometric reaction. But from a balanced stoichiometric reaction, we cannot determine the order of reaction. Order of reaction can only be determined experimentally. That is why X was not in the previous equation I wrote on the board. So it means we have already determined that this reaction is at X order. So order values in the reaction does not contribute to order of reaction. So the order of reaction will have been given in the question, or you would know the order of reaction depending on the unit of your rate constant. So let me start from there. Rate constant. Rate constant K. It has different units for different order. If you have K, let me say K0, that means K in zero order. The unit is mole per dm³ per second. From this particular equation, you will discover that our concentration will be in mole per dm³, while our time will be in seconds. So bringing the two together is going to give you mole per dm³ per second. That's number one. If your K is in first order, the unit will be per second, just per second. If it is in second order, the unit will be per mole per dm³. Per mole per dm³ per second. So this is zero order, first order, and second order. The unit of K. So if you're given a question and you are given the rate constant, the unit of rate constant will even let you know the order of reaction. If the unit of your rate constant is mole per dm³ per second, then you know that, of course, this reaction is zero order. If the unit is per second, it is first order. If it is this, it is what? Second order. Now, how do we now compare rate and concentration? Because that is our main concern in this topic. How does rate? Because we have explained how other factors affect rate of reaction, but we have not established how concentration affects. Now, if we have a reaction at first order, R is equals to K, A raised to power 0. It means this reaction is zero order in respect to reactant A. Whatever reaction that produces A or in which A is existing, let me rewrite the equation normally. We have AA plus BB to give CC plus DD. Now, in this reaction, now it shows that reactant A is zero order. Just reactant A is zero order because we have R to be equal to Ka raised to power 0. The power of your concentration is what we call order of reaction. So if this 0 is removed and we replace it with 1, it shows that A is first order. If this is removed and we change to 2, it means this reaction is second order in respect to A. So any language they use, just know that this particular power represents order of reaction. Now, if the concentration of A is increased from a particular value to another value, what happens to the rate? That means we are increasing concentration, what happens to the rate? Let us do it this way. R is equals to K, 1. That means concentration is 1 at this point. Concentration is 1. So everything here will also be 1. Because K is constant, let's leave it out. Now, if the concentration is doubled, that means it will now be 2. R is equals to K. Instead of 1, we have doubled it. Raised to power 0. Everything here will also be 1. That means even if the concentration of a particular substance at 0 order is doubled, the rate remains the same. So that is why I was saying the other time that it's not every time that you increase either any of the factors that the rate will also increase. But if you look at pressure, temperature, catalyst, and nature of reactant, once they increase, rate of reaction increase. But concentration, if it increases, rate of reaction may not increase. Now, a very good example is for zero order reaction. In reaction at zero order, if the concentration is increased, rate remains the same. That means concentration does not have effect on the rate of the reaction at zero order. Concentration does not affect the rate of reaction at zero order. If the rate is increased, if the concentration increases, rate remains the same for a zero order reaction. Now, for a first order reaction, if the concentration is increased, what happens to the rate? That means we are going to have R to be equals to K. Let's use the same A raised to power 1. Now, if the concentration is 1, that means our answer will be 1. If the concentration is doubled, R equals K into 2. It is doubled now, raised to power 1. Our answer will be equals to 2. This is to tell us that if you double the concentration of a reaction at first order, the rate will also double. Now, we have finally come to a particular site where increase in concentration also increases rates. In the one we explain for zero order, increase in concentration does not increase rate. But this time around, we even doubled the concentration and the rate also doubles. If we multiply by 3, let's say we triple it, the rate will also triple. So it is telling you that for a first order reaction, the ratio at which we increase concentration is also the ratio at which the rate will also be increased. If you multiply it by 1,000, rate will also be 1,000. So it means once you increase concentration, the rate will also increase accordingly for a first order reaction. What if we try for a second order reaction? This is 1, this will now be 2. Then if this is 2, this will also be 2. Our answer here will be 1, while our answer here will be 4. Because we have doubled it. We doubled the concentration of a second order reaction. The rate here will be 1, the rate here will be 4. So this is to tell you that if you are going to put it into writing, if the concentration of a second order reaction is doubled, the rate quadruples because it is 4. the rate quadruples. If it is, let's say initially here we have 2, our answer will be 4. If you double, when you double 2, it becomes 4. Our answer here will be 16. You can see it is multiplied by 4. So if the rate of the second order reaction is double the concentration, so if the concentration rather of the second order reaction doubles, the rate quadruples. So that is how concentration affect rate of reaction. It is not every time that you increase concentration that the rate of reaction increases. A very good example is that of zero order. If you increase concentration with any ratio, the rate is not going to change if the reaction is at zero order, because everything will be raised to power 0 and it will be 1. But for first and second order, if you increase concentration, rate also increases. But it increases faster for a second order reaction compared to that of a first order reaction. Now, there are so many other parameters that we may want to look at in this aspect of expressing rate of reaction, because you may be asked to calculate some parameters like time, half-life, T, which is represented as T half, initial concentration A naught, and final concentration AT. This is time, this is T half, which is half-life, A naught is initial concentration, AT is final concentration. You may be asked to calculate any of these things. Now, each of those order of reaction has its own formula. For zero order, for a zero order reaction, we have T half to be equals to A naught over 2K. That means initial concentration over 2K for a second order reaction. This is the relationship between half-life and concentration. Now, don't forget that for a zero order reaction the other time, we said the rate does not depend on concentration, because no matter how much you increase the concentration, the rate is not going to increase. But the half-life depends on concentration. So you have to make sure you be careful, because it may be tested on those particular postulations that, okay, for a zero order reaction, the rate does not depend on concentration. That same zero order reaction, the half-life depends on initial concentration of reactant. So, secondly, the second formula we have for zero order, we have A naught, concentration of A naught, to be equals to minus KT plus final concentration. Please, you can see. Initial concentration equals minus KT plus final concentration. Now, we used to have a graph for this. If you compare this with equation of straight line graph, which is y equals mx plus c. This y means what you are plotting on y-axis. M is your gradient, which is slope. Your x is what you plot on x-axis. Your c is intercept on y-axis. That means if you have a plot like this, from this expression, we are plotting A naught on y-axis. So we're going to have A naught here, concentration of A naught. We have T on x-axis, because T correlates with where we have x. We have T here. Now, our graph will actually be a linear graph, because what we are plotting against each other in the equation, they are both directly proportional to each other. They are both directly proportional. So it means to be a linear graph, but the slope is negative. That means we're going to have something like this, negative slope. So this intercept is where you're going to have concentration of AT. That is for a zero order reaction. Now, for a first order reaction, the change is not too much, just little change. T half for first order reaction is ln 2 over K, or if you press ln 2 on your calculator, you have 0.693 over K. Now, the argument is this. For a first order reaction, the rate depends on concentration, because once you increase concentration, rate also increases. But the half-life does not depend on concentration, because you can't see half-life in this relation. Sorry, you can't see concentration in this relation. So take note of those things. Now, for the integrated rate law, it's going to be ln A naught is equals to ln AT. That is just the difference. It is still the same thing. Lin A naught, lin 80, that's just the change. So we're going to come here to change this one to lin A naught. We are plotting it against T, and this one will be lin 80. To still be a negative slope, the same thing like that. And we have another formula for first order again. We have K is equals to 2.303 over T log A over A minus X. A here represents initial concentration, while A minus X represents final concentration. So I've already said I'm going to explain zero and first order. So this is for zero order and first order, the explanation and the possible formulas you will need for calculation. In the next video, I will be bringing examples to calculate. I will also explain second and third order. Thank you.